Okay. Finish. Realize if I have taking coffee and sandwiches in my class, people will be here earlier. More, right? So, yesterday we have covered two things. One was superelevation, the other one was spiral transition curve. Okay, and they are related to each other, as superelevation is often given on the spiral transition curve. Okay, so we looked at the calculation related to distance required for doing the superelevation, and the things related to spiral transition curve, how to calculate its length, and the other points on the other important points related to this curve. Today we will start with the discussion of the side distance. Okay, side distance is the most important part of the highway design. Okay, important in terms of what? Safety. Okay, important in terms of safety. So, side distance on a straight road is much easier to accomplish than any curve segment. Okay, and the reason is, on a straight road, if I'm looking ahead, okay, and there is nothing blocking my view, I have the full side distance, right? If the road is 2 kilometers and my eyes allow it, I can see up to 2 kilometers, right? No problem. And obviously on the road we are designing the road for traffic. So by default there would be nothing in front of it, right? Okay, apart from the fact that you give a bridge or something, but that is also very high. Okay, so in most of the cases for straight roads we don't have to worry about the side distance. Okay, it becomes a problem on the curved segments. Why? So you look here, so this is a curve. Okay, let's say I'm driving in this lane. Okay, can I see what is happening on the other side? No, why not? Because of trees, right? So we should cut down all the trees in the wood, right? No? Now where is the tree? On the road? No, on the side. Okay, so this is the problem we have, that something which is not even on the road is blocking my view. Okay, so in order to maintain side distance on the road, I have to take care of the side of the road as well. This is an extra point we need to take into account. So how do we do this? How do we take care of the side distance? By maintaining something on the side of the road. It looks like you are coming in airplane with refreshment or something, right? No? You should. Okay. So this is the curve, and let's say to make this curve safe, I need a side distance equal to S. This is my required side distance. Okay. How to calculate the side distance? We have already talked about it in the previous topic. How to calculate stopping side distance, decision side distance, passing side distance. Okay. So the required, we know how to calculate, or I know how to calculate. I cannot trust you, right? I know how to calculate it. Okay. So this is what I need. So according to this much distance, if I am here, I should be able to see up to this point, right? There. So to make this much distance clear on the curve, I need this much distance clear on the side. Okay. This is the clear distance I need on the curve, because I will be looking on the other side like this. Okay. The straight line. Okay. So to make enough distance clear on the road, I need this much distance clear on the side so that I can see it with my eyes. My line of sight, the straight line of sight. Okay. So this is the curve. And what do we call this line? Chord. Okay. So the side distance is the curve and your line of sight is the chord. Clear? The distance between them, m mentioned here, is called as the middle ordinate. Okay. And we saw it is one of the components of the horizontal curve. Middle ordinate, the distance between the curve and the chord. Okay. Also called as horizontal sight line offset. So m is another name for horizontal sight line offset. Clear? So when I call it m or middle ordinate or horizontal sight line offset, the first equation is the equation we already know from the horizontal curve. Okay. The middle ordinate, the distance between the curve and the chord for any circular curve is calculated using the first equation. Okay, I've already showed you earlier, we calculated m in one of the previous examples, and obviously you don't remember. Okay, so m I know how to calculate. Okay, now I have r means radius, and delta is what? What is delta? Angle of intersection. Okay, deflection angle or angle of intersection. Okay. Now I want this m along a curve, right? And what is the length of this curve? Side distance. Okay. I want my curve to be as long as the side distance. Okay. How to calculate the length of the curve? This is the equation. This is the equation for calculating length of the curve. Okay. It is lex. What happened? Sorry, I disturbed. Okay. So I want this length to be equal to what? What is this? Side distance. Okay. So now I have an equation for side distance equals to this whole thing. Okay. And I will make this equation for delta. So I take delta on one side, everything else on the other side. Okay. So I will get delta in terms of side distance. Okay. Do you see delta in the first equation? Okay. So I will replace delta now with this whole thing. Okay. So m will become in terms of side distance. Clear? Okay. And this is the equation. M in terms of side distance. Clear? Okay. Now in this equation I have R and I have D both. Okay. But I know R equals to this upon D. So I can replace R with this ratio. The whole equation will be in terms of D only. What was D? What is D? Degree of the curve. Okay. So the whole equation is in terms of degree of the curve. This is one way of doing it. Another way of, don't replace R, replace D. Okay, so D will become in terms of R. Okay, so you can use this equation where you need R and D both. You can use this equation where you only need R, or you can use this equation where you will only need D. Okay, depends upon how you want to use it. All of them give the same answer. And this is the equation for what? Which side distance? Which side distance? We have discussed different types of side distance, right?
Yeah,
Huh?
yeah.
It's on the curve, yes. But what type of side distance? Huh? Stopping, decision, passing, intersection. Huh? Very innovative. Why passing? This equation is for which one? Look at the equation, for God's sake. This equation is for which side distance? Decision. What decision? To reduce or stop. Okay, good enough. Okay, this is for stopping. Okay, the easiest one, the most common one, the one which you have used always. Okay, I did not even discuss the equation of passing that distance. I did not even show it to you. And there is not a single equation for passing that distance. Same thing for decision. Okay, decision side distance have two different cases or different equations. Okay, this one is for stopping, normal stopping or decision stopping, whatever. But it's for stopping. Okay, why it is mentioned? Because this is the minimum. Is the minimum we need. Okay, we could need passing. Okay, we could need something else, but this is what we need always. Okay, that's why it's written here. Okay, we have a 6-degree curve, and this curve is for the inside lane. Okay, this curve is for the inside lane. Now you look at this road has 3 lanes, right? Okay, all of them are on the curve. Okay. Which lane has the most critical value here? The inside lane, right? The one which is closest to the tree. Okay, this one is even farther, right? So this driver can see more, and this one is even farther, so this driver can see more. So whenever we are checking the side distance on the curve, we are doing it for the inside lane. Okay, other lanes is understood. If this is fine, the others are also fine. Clear? Okay, the most critical one is the inside lane. Clear or not? She just woke up. Clear?
Yes.
Okay.
So if the cap is turning left, so it will be
Inside lane of that side, yes. Okay. So that's why the inside lane is given. So the curve will have a speed of 70 miles per hour. There is no gradient. Driver reaction time normal 2.5 seconds. And we will use H2 recommended braking deceleration. And what is the closest any roadside object can be placed to the center line of this lane? Okay, so they are asking for M. Okay, to calculate M, first of all, I need to calculate the side distance. Okay, this is the equation for side distance. S is 70 miles per hour, T is 2.5 seconds, and this factor is already according to the H2 recommended braking deceleration. So how much is ds? Okay, so now we can calculate M. Okay, since they give me the degree of the curve, so I will use this equation, 6 degrees. Okay, so ds 6. So what is M now? Uh, 68.3. Okay, any questions? So to make this curve safe for 70 miles per hour, don't place anything within 68.3 feet of the inside lane. Okay, if you do, the driver in the inside lane will not have enough side distance. Clear? Okay. Yeah. Up till now we have discussed circular curve and we have discussed spiral transition curve. Okay. Are they of the same type or different types? Huh? Different. Okay. Why they are different? What's the difference between a spiral curve and circular curve? Yeah, the radius changes for the spiral curve. Okay. But you join them together. Whenever you use it, you join them together. Okay. But there is another combination where you join 2 circular curves together, 2 or 3 circular curves together. Okay. So this combination is also possible. Okay. So this combination is called as compound curve, where you are joining 2 or 3 circular curves. Okay. So the joining of a spiral with circular is not compound. It's not called compound. Okay. Compound is when you join two or more circular curves. Clear? And each circular curve will have its own radius, right? Why do we do it? We do it for the for saving space. Okay, if you have two tangents and to cover the angle between the tangents, if you decide I will cover it using single curve, it will need more space. Compound curve will need less space as compared to a single curve. Okay, so that's why we do it, especially for ramps. Okay, because in case of ramps, then you are building it in the air, right? It's like a whole structure, so it will cost more. Okay, and it may disturb the buildings. It will need something. It may be going to a underpass or something. Okay, so then because of the money and so on, then you may have to do it. Okay, but in terms of construction or in terms of the driver, which one is easier, single or compound? Single is easier. Okay, so there are some cases where we have to use it. Now, what is happening on the compound curve? The driver is going from tangent to one curve to the other curve, and then maybe to another curve, and then to the tangent, right? So we want to make it easier for the driver to do this whole process. So you cannot just join any two curves which you want. Okay? So there are some restrictions on which curves you can join together. These curves should be closer to each other. Okay? Like in terms of radius. In terms of curvature, they are not the same, but they are closer to each other. What do we consider as close to each other? When the radius of one curve to the other is not more than 1.5 times. So the two curves which are joining together, the ratio of their radius should not be more than 1.5. So if you have a curve of 1000, the other one should not be more than 1500. Clear? Okay. So this is when you are comparing between radii. But you may compare between degree of the curvature as well, like we did in the previous example. You have an equation with radius, you have an equation with d as well. Okay. So let's say you don't know the radius or you know the degree of the curvature. So what is the comparison for degree of the curvature? The difference in degree of the curvature should not be more than 5 degrees. Somebody told you I want to join these two curves and he gives you two radii, the values of the radius, then you will use the ratio 1.5 times. If that person gives you the degree of the curvature for both the curves, then you will see the difference between them. Okay, and the difference should not be more than 5 degrees. Okay. It may happen that the two curves are not directly joined together. So there is some space between them. You have a curve. Okay, space means it's a straight line. Huh? Space doesn't mean space. It's still a car, huh? Not an airplane. So no space. It's a straight line. Okay. So that if that straight line, okay, that tangent between the two curves is less than or equal to 200 feet, this arrangement will still be called as compound curve. You will still consider as a compound curve. You will design it as single because these two curves are now separate. You will design them accordingly. Okay, you have to consider the straight part between them. Okay, but this whole thing will be considered as a compound curve. So you have to still maintain the ratio. Okay, you cannot say this one is 100 feet from this one, so I will design them separately. No, this is still compound. These ratios and differences will still apply. These requirements will still apply. Got it?
Yes.
Okay. So two curves or three curves which are directly joined together, or they have a small tangent between them. Okay.
What is the small tangent measured from?
Sorry, from the end of one curve to the start of the other. It's not here. There is no tangent. It's one curve and the next one is directly connected. Okay, so clear? Then we have reverse horizontal curve as well. Again, we are joining two circular curves together. Okay, so here when I was joining the curves together, each curve had a different radius. Okay. In a reverse curve, I am joining two curves together which have the same radius but different direction. Okay, same radius, same direction, then it will be a single curve. Okay, so we have two curves, this one and this one. Both of them have the same radius, but they are going in different ways. Clear? Yeah, so this one is called as a reverse curve. So in a reverse curve, you basically make the driver go through whole 180 degrees. From the start to the end, the total angle is 180 degrees because you are doing the half circle. Okay, this is, both of them are equal to half of a circle. Okay, so you make the driver go the entire half circle. Okay, which could be complicated. So we, in order to make this transition safe and comfortable for the driver, we do two things. First of all, we insert a small tangent between the two curves which we are joining. Here it is required now. It's not optional. Here it is required. Okay, but it should be a small tangent, otherwise those two curves will be separate. Okay, so in a reverse curve we put a tangent, okay, and that tangent should be again the same limit, 200 feet or less. Okay, and secondly, we also insert a, not one, like at the start and end of every curve you have a spiral transition curve. Okay, again to make the turning gradual, more comfortable. Clear? Okay. So we have the compound curves, different radii, same direction. We have the reverse curve, same radii, different directions. Okay, and in this case, then we have to take some extra measures. Okay, now we move towards the vertical alignment of the highways. As I already mentioned, vertical alignment, if you are looking at the road from the profile, again you will see straight lines and curves. The straight lines are called as grades and they are shown as percentage. Okay, so this 4% means 100 feet length and 4 feet difference in elevation. Okay, and it could be positive, it could be negative. Upgrade is considered positive, downgrade is considered as negative. Okay, and what else? Yeah, so this is about the grades, the straight lines, and wherever you are going from one grade to another grade, you have to join it with the vertical curve. Okay, the shape of the vertical curve is parabolic. Okay, what was the shape of the horizontal curve? Circular. Okay, so this is a parabolic curve. So parabolic curve have higher degree than a circular curve. Okay, a circular curve is simpler as compared to a parabolic curve. Okay, so this is also already a higher degree curve, so there is no spiral transition curve here. Okay, this is enough for the transition. It provides a smooth transition for the drivers on the vertical curves, or going from one gradient to the other. Going back to the gradient, how do I decide the gradient? We have this table which tells you the gradient to be adopted according to the type of road you have, according to the terrain you have, and according to your design speed. Okay, so for example, I am doing a rural arterial. Okay, and I am doing it in a mountainous area. Okay, and my speed is 50 miles per hour. So my gradient will be 7%. Okay, now can I do less than 7?
No.
No?
Yes,
Yes.
the maximum is 7.
Huh?
Maximum is 7.
Maximum is 7. Okay, well, the other answer was I can do whatever I want, right?
There is 10 also.
Sorry?
There is 10 also.
Where?
The overall character.
Yeah, it's a different type of road. Right? Clear? Okay, so this is maximum value. Some values you can see not applicable, that means the combination is not applicable. It's a combination, right? Every value is a combination. Combination of road type, terrain and speed. Okay, so the values which are not given in their standards, this combination is not available. Okay, to have a rural, to have an urban arterial in a mountainous area with a speed of 80 miles per hour is not available in their standards or in their data. Okay, you want to do it, you can do the calculations yourself.
Can happen or can arterial and mountainous in the speed of 80. Can?
It shouldn't. Okay, because why do you call an area urban? It's populated, right? Then it will not be, even if it was mountainous, you will, very good. I said, get rid of the mountain. Come on. This means kill everybody? Okay. Another thing you have to consider when deciding the gradient is the effect of gradient on trucks. Okay. Now which one is more critical for the trucks, going upward or downward? Huh? Upward, okay, because on upward they will be going what? What will happen when they try to go upward? They will
Slide down.
be slower, right? Okay, so their speed will keep on decreasing, and you may have seen as they keep on going up, the speed keeps on reducing, okay, until they reach a very, very low comfortable value, okay, and then they continue at that value. Okay, so this graph shows you that phenomena, that the curve, the gradient starts somewhere here, the truck enters the gradient, and as the truck is moving on the gradient, it is reducing the speed, okay, until it reaches some low value which it can maintain throughout the gradient, okay. You can see that value as well. Okay, so you need to consider how much reduction will there be on the curve, okay, for the trucks. You're designing a 2-lane road, you will say that I'm designing it for a speed of 60 miles per hour and I'm making a gradient of 9%. Okay, so even one truck enters on this gradient, okay, you can see the fall in speed. How rapid is it? Quickly falling down up to less than 20. Okay, so this road will not maintain the speed you are looking for. Okay, one more thing you can observe, these are different gradients. So the reduction is less when the gradient is less. Okay, so going upward on a high gradient will have more reduction in the speed. Okay, and another thing you can see is the reduction is very subtle, gradual. Here the reduction is very steep, okay, sudden drop. Okay, so these points should also be kept in mind. Normally we the critical length, yes. So there is a critical length of any gradient which you can allow on the road to have acceptable reduction in the speed of the truck. Okay, so critical length is the length of the gradient which you allow on the road up to which the reduction in the speed of the truck is acceptable for you. Okay, and how much is that? That is between 10 to 15 miles per hour. Normally we can allow the reduction in the speed of the trucks from their original value up to 10 to 15 miles per hour. Okay, from the original value, from the initial value. Okay, so from the initial value, if it goes less than 10-15 miles per hour, it is considered acceptable. Okay, so how do I know the critical length? How do I know that up to which length this reduction will happen? So we have this graph which shows you for every gradient how much length will give you a specific reduction in speed. So these 5, 10, 15 are the reduction in speeds of the truck. Okay, a normal single unit truck. Okay, so this curve is for a 5 miles per hour reduction. So if I have a 2% gradient, okay, and I'm saying I will restrict the reduction up to 5 miles, then my length should not be more than this. Clear? Okay. Let us look at an example. We have a rural freeway in rolling terrain, speed of 60 miles per hour. Rural and rolling terrain, rural freeway, rolling terrain, speed of 60 miles per hour. Asking for the longest means the length, how much length we can give, and the steepest means the value, the gradient itself. Okay, so how long you can give the gradient and how much you can give the gradient. Okay, so first of all, let us decide about the value. We'll use this table. Where is rural freeway? Is here at the end. My terrain is rolling. This one. My speed is 60. 4%. Okay. For 4% gradient, how long can it be? Okay, so let's say we allow a decrease of speed up to 15 miles per hour for the truck. Okay. So 4% gradient, and go up to the curve of 15 miles per hour. This is the longest it can be. Okay, a curve of 4% can go up to this much length. If you go more than this, then the reduction in speed will be unacceptable. It will be more. Okay, more than allowed. Now let's say you say that I cannot give a gradient of this much. I cannot give a length of this much. Okay, then I will reduce the gradient. I reduce the gradient. Okay, yes, we can change the speed as well. Yes. So let's say, because reduction is possible, right? I don't have to change anything on the road. 4% was maximum. I can give 3%. Okay, so if somebody gives 3% for the same road and 15 miles per hour reduction, so 3%, where is 15 miles per hour? Here. Okay, so the length increases. You can make the length up to this much now. Almost 3000. It was less than 2000, now it's almost 3000. Clear? Okay, so this is how you can manage these values. Okay, the other thing which you see in the vertical alignment or the profile are the vertical curves. Wherever the gradient is changing, you have to provide a vertical curve. Okay, vertical curve has two main types, and then each main type has two subtypes. Okay, the first two are called crest, and the last two are called sag. Okay, and you can see why they are called crest and sag, because of what is the shape of the vertical curve? Parabola. All of them are parabola, but because of the yes tangent, very good. I like it. Yes. Yes. Huh? The turn. Okay.
To get down and to get up.
Yes. To curve up, to curve down. Okay. The direction, right? The direction. Okay. So we said each main type has two subtypes, right? So this is subtype number 1, this subtype number 2. Okay. And what is the difference between them? Both of them are crest. Both of them belong to the crest category. But why they are different?
Two positive gradients or two negative ones.
Yes. Okay. In type 1, you have gradients in different directions. One of them positive, one of them negative. Okay. In type 2, both of them are positive or both of them are negative. Okay. Same thing for the sag curve as well. You can have a sag curve with gradients in different directions, or you can have a sag curve with gradients in same direction. Okay. So type 1, crest, gradients in different direction. Type 2, crest, gradients in same direction. Type 3, sag, different directions. Type 4, sag, gradients, same direction. Clear? Okay. Now, if somebody gives you two gradients, for example, the value of gradient 1 and gradient 2. Okay. Now, how do you know it is crest or sag? You don't have these figures. There is no sketch. You just have two values of the gradients.
Where it starts, if it starts in positive.
No other
and
thing.
negative,
Yes.
If it starts in positive then negative,
Mm-hmm.
so it will be.
And if both of them are positive, then huh? If first one is more, then it's what?
Crest.
Crest. Okay. If G1 is more, the first one is more, it's a crest curve. If G2 is more, that's a sag curve. Okay. So if you are going from +4 to -2, it's crest. Okay. -2 to +4, it is sag. +2 to +4, sag. Okay. Going from lower to higher, sag. And -2 to -4, crest. -2 is higher. Okay. When the minus comes, it becomes lower. Okay. Got it?
Yes.
Sure. So some points. Okay. Let's see the points in this figure. So there are three main points. For a vertical curve, there are three main points. All of them have these three main points. The first point, which is VPC, vertical point of curvature or vertical point of commencement. The one which is in the middle at the intersection of the gradients, which is VPI, vertical point of intersection. And the last one, okay, the last point of the curve, VPT, vertical point of tangent or vertical point of termination. Okay, they are joining the two gradients G1 and G2. Okay, the length of the vertical curve is L. Okay, and VPI, the point of intersection, is in the middle, is aligned with the middle, not on the curve, aligned with the middle of the curve. Okay, so from the start to the intersection is L by 2. Okay, and the remaining is also L by 2. Clear? Okay. Then we have a parameter, we will not use it, but it's used in some other equations in books, which is called A, which gives you the absolute difference between the two gradients. The absolute difference between the two gradients. Okay. This is what? Equation of a parabola. Okay. And why it is written here?
Because our curve, the vertical curve is parallel.
Vertical curve is parabolic. Okay. So in this equation we have y and x. Each point has some elevation, which is y, and each point has a distance from the start point, which is x. Okay. So for each point we have a value of y and x. Okay. Then we have three constants over here, a, b, and c. Okay. These are three constants for the whole curve. Okay. A, b, c are constants for the whole curve. So in order to use this equation for any point on the curve, I need to find out the value of a, b, and c. Okay. So let's start with taking the derivative of the equation. Okay. You take the derivative, it becomes this. Okay. Now derivative dy by dx is what?
Tangent.
Tangent?
No.
Gradient, slope. Okay. Tangent theta. Fine. Okay. Now when x is 0, distance is 0, which point of the curve I am standing on? VPC, the start point. When x is 0, I am at the start point. When I am at the start point, what is my gradient?
G1.
Right? Okay. At the start point, the gradient is G1, right? I am starting from G1 and going up to G2. Okay. So at the start point, my gradient is G1. Okay. So this is the gradient. I'll put x equals to 0. When x is 0, this whole thing should be equal to G1. Okay, so this gives me 2x equals to G1, where x is 0. So then it remains b equals to G1. Clear? Okay, so I found the value of b, which is the first gradient. Okay, then I will take the second derivative of this equation. So if the first derivative was the slope, the second derivative will be what? No. Angle. No. We will use it, yes, but not the second derivative. The first derivative was the slope, right?
Yes.
The first derivative was the slope. Derivative means what? Derivative in general. Why is this term is in our lives? Apart from, making our lives difficult. What is the use of this term? Why do we need derivative? Derivative means what? And they told you in the maths courses you were sleeping, right? He is talking about derivative. Who needs it, right? Derivative is the rate of change in something. Derivative of the, yes, now I remember, it was in my dreams. Okay, rate of change in something. Okay, change in what? Change in the thing which you are taking the derivative of. So here I am taking the derivative of what? This is what? Slope. Okay, second derivative is the rate of change in slope. Okay, this was the rate of change of what? This one is rate of change of what? No, this one right now. Rate is written. It's like at the edge of my finger. Rate of change of what?
It's right there.
This is my finger. And this. Rate of change of elevation. Thank God. You guys found my finger. Okay. last person on earth to tell you these things. Okay. So rate of change of slope, right? Rate of change of slope. What is the change in slope? G2 minus G. Rate of change of slope means just divide by length. Okay. Clear? So the first derivative was 2ax plus b. Second derivative 2a. So this is the rate of change of slope. Means 2a equals to this. So a equals to. Clear? Okay. So there were three constants a, b, and c. I took the first derivative, I got b. I took the second derivative, I got c. A. Okay. Now for c, I will take third derivative. Very good. Okay. Yes, we will take third derivative. Third derivative will be what? 0, right?
We have a and we have a, so we can find it.
So we can just you can do anything you want, right? Okay. For c, I'll go back to the initial equation. So no derivative. Okay. I'll go back to the initial equation. Okay. In this equation, if I put x equals to 0, then y equals to. And we said when x equals to 0, I am at BPC. Okay. So that means y equals to c or c equals to y. Y of what? BPC. Okay. So c is the elevation or y of BPC. Clear? Okay. Everybody clear? Okay. Now somebody said we put slope equals to 0. Yes, we will put slope equals to 0. When do we put slope equal to 0? Maximum point. Okay. So I already have the equation for slope dy by dx, right? In that equation there was 2ax plus b. It was 2ax plus b. Okay. Now I know the value of a and now I know the value of b. Okay. So instead of keeping it 2x plus b, I'll put the things for a and b. So b will be this one and a will be that. Okay. So 2x plus b, I'll put the values for a and b, and now this should be equal to, this whole thing should be equal to 0. Okay. So this will give me the equation for x. Clear? What is x? The distance at which you have the highest or the lowest point. Clear? Clear? Okay. So we are, yes. Vertical. No, sorry, horizontal. Horizontal. X, horizontal. Vertical is what? Y. Okay. Now look at these curves. Okay. For this curve, where is the lowest point? Huh? No, for the curve. For the curve. Point of intersection is not on the curve, right? So it's somewhere on the curve. Okay, we don't know. So for this one, I have to use the equation because I don't know exactly where is the lowest point. Same thing for type 1 as well. I don't know where exactly is the highest point. Okay. But for these curves, where is the highest point? Huh? VPT, right? Okay, VPT. And for this one, it is the highest point is VPC. And if I'm talking about this one, the reverse, right? Lowest point is VPC and the highest point is VPT. Okay. So if both gradients are positive, I know I'm going upward. So this is my lowest, this is my highest. If both are negative, I know I'm going downward. This is my lowest, this is my highest. I don't need any equation. Okay. I don't need any equation means that you don't cry when something like this comes in the exam. Doctor, you cannot find it. You said there was no equation. There is no equation because you don't need it. You already know VPC and VPT. So one of them will be highest, one of them will be lowest. There is a highest and lowest point. Okay, it's VPC or VPT. Clear? You only need the equation for type 1 and 3. Okay. Okay, let us look at this question. We have vertical curve 600 feet. Joining 4% to minus 2%. Elevation of VPC is given. Start point is given. Okay. Yes, yes. Don't even ask. Okay. This is what happens in the exam as well, right? Forget about the question.
Yes.
I know what I need to write. I had a friend like this. In final year, he got mad. So we literally. Okay. Then he was treated. He came back. Okay. Then he finished the engineering. So you have good future. You will do engineering in the end. Okay, so we need 3 points here: point of intersection, high point on the curve, and VPT. Okay, let us start with VPT and VPI. Okay, because for them we already know the data. Okay, VPI. Okay, if you look at this figure, I am at VPC. I know the elevation of VPC. I am going to VPI. Between them, the gradient is G1. Between them, the distance is L by 2. Okay, so I know the initial elevation, I know the distance, I know the gradient. Okay. So VPI elevation is VPT, which is 1250 plus. Why plus? Because the first gradient is upward, so I'm going up. Okay. How much is this? And for VPT, I will go down from VPI. How much is VPI? 1262. 1262, yes. Okay, now for VPT, I am coming from VPI going down, right? Why down? Because the gradient is minus. Okay, so it will be 0.02. How much is this? 1256. Okay, now they are asking for the highest point. Okay, for highest point, first of all I should know the x for the highest point. Okay, this is the equation. Okay, don't worry about the negative sign, just put everything as it is. Okay, if it is negative, you put negative. This is 4 positive, you put 4. And this one is 2, okay, minus 2, okay, and 4. Keep the signs as it is. Okay, it will cancel out. But keep in mind, this equation is only when we have gradients in different directions. Both of them are positive, both of them are negative, then you will not use the equation. Okay. If you try to use it, you will get negative sign. Then you know that you did something wrong. He is delaying us because of him. Everybody will be late. What?
1208.
He is wrong. Do it. Yes. 400. Okay, so the distance for the highest point is 400. Okay, now I need to find out where, what is the elevation of the highest point. So for that I will use the equation of parabola. Okay, in the equation I have A, B and C. Okay, so B is the first gradient, which is 0.04. Okay, A was the difference in gradient upon the length. So we have 5. Okay, because we don't have time. Okay, it's something like this. Okay, and the C is the elevation of VPC. C is the elevation of VPC, which is already given. Okay, so C is 1250. Okay, now the equation of the parabola is ready. Okay, so I will find out y. Okay, it was ax square. So A is okay, plus bx plus C. This will give you the elevation of the highest point. Huh? Say again. No, no, my multiply by 10. 10, sorry, 10. To the power.
12.
Recheck the answers, okay? I'm not writing the answers because I'm just writing the values from my mind. Okay, so I can use the same equation, okay, for finding out the VPT elevation as well. Then I will put x equals to the length of the curve, because VPT is the end of the curve, right? So x will become the length. So for VPT we have two methods, this one and this one, okay? For the highest point, can I use this method? For the highest point, can I use this method? I cannot, okay? Because the highest point is not on a straight line. This method works on a straight line, okay? So for the highest point, you have only one thing, okay? And the last point is, why are we checking for highest point and lowest point? People who were with us in the site visits as well, they were mentioning something about the planning, okay? Any site visit. They were mentioning about the planning. Sometimes they are constructing the road and they find some utilities are under the ground. Okay, or maybe you are constructing the road and there's a bridge over there, or there will be a bridge in future. Okay, so that's why we check the elevation of the highest and the lowest point, so we know in advance that my road will not cut down any utilities or intersect with any bridge or be close to any bridge or something. Okay, so that's the point of checking the highest or the lowest point. Make the bridge and so you need to still you need to know, right? To make the bridge higher, you need to know how much is it. So this is what we are doing. Sorry?
I will find x 400.
Show us like what is that?
Who gave me the value? The value is correct. You can show me.